Welcome to this video on occupational health and hygiene. We will be discussing physical hazards, specifically focusing on ionizing radiation. Ionizing radiation consists of subatomic particles and electromagnetic waves that are emitted during the natural decay of unstable atomic nuclei. As these unstable atoms attempt to achieve balance, they release energy in the form of radiation. Understanding how this energy interacts with matter is fundamental to identifying workplace risks, implementing effective controls, and protecting personnel working in hazardous environments. Let us dive into the specific types of ionizing radiation and their behaviors. Ionizing radiation manifests in 5 primary forms that safety professionals must manage. First, we have alpha particles, which are relatively heavy subatomic particles. Second are beta particles, which are fast-moving electrons or positrons. Third, we have neutrons, uncharged particles that possess high penetrating capability. Finally, there are gamma rays and X-rays, both of which are high-energy forms of electromagnetic radiation. Each type of radiation originates from different atomic processes, behaves differently in air, and presents distinct risks to biological tissue, making individual hazard assessment essential. Let us look closer at how these forms are categorized. Alpha particles, beta particles, and neutrons are directly emitted by unstable radioisotopes, also known as radionuclides. When an unstable radionuclide decays, its atomic structure reconfigures, discharging these particulate emissions into the surrounding environment. Because these particles carry mass and electrical charge, or, in the case of neutrons, significant kinetic energy, they interact heavily with matter in their path. Managing radionuclides requires strict contamination controls to prevent workers from inhaling, ingesting, or absorbing these particle-emitting substances into their bodies. In contrast to particulate emissions, gamma rays and X-rays represent the waveform of ionizing radiation, specifically high-energy electromagnetic radiation. While gamma rays originate directly from the decaying nucleus of a radionuclide, X-rays are typically produced machine-generatively when electrons interact outside the nucleus. Both forms consist of photons traveling at the speed of light with no physical mass or electrical charge. Due to these wave properties, electromagnetic radiation can travel vast distances through the air and easily pass through many common materials, requiring dense shielding solutions like lead or thick concrete. To understand radiation better, we examine the full electromagnetic spectrum. Radiation spans a vast range of wavelengths and frequencies, scaled relative to real-world objects, from radio waves with wavelengths as large as buildings, down to gamma rays with wavelengths smaller than an atomic nucleus. As we move from left to right across the spectrum, from radio, microwaves, infrared, and visible light, to ultraviolet, X-rays, and gamma rays, the wavelength decreases while frequency and energy dramatically increase. Higher frequency means significantly higher energy per photon, which dictates whether radiation can damage biological matter at a microscopic level. This distinction brings us to the critical threshold on the spectrum, the boundary between non-ionizing and ionizing radiation. Non-ionizing radiation, including radio waves, microwaves, infrared, visible light, and lower frequency ultraviolet, has enough energy to excite molecules, but not enough to strip electrons from atoms. Once we cross the threshold into high-frequency ultraviolet, X-rays, and gamma rays, the energy level becomes high enough to cause ionization. This ability to strip tightly bound electrons away from atoms creates free radicals, breaks chemical bonds, and damages biological tissue at the cellular and genetic levels. A fundamental concept in radiological protection is half-life. Half-life is defined as the time required for the activity of a radionuclide to decay to exactly half of its initial value. As shown on the decay curve, as the number of elapsed half-lives increases, the remaining fraction of activity predictably decreases, from 1.0 down to 0.5 after one half-life, 0.25 after 2, and so forth. Understanding half-lives is crucial for occupational hygiene, as it determines how long radioactive materials remain hazardous and dictates the long-term storage and disposal strategies for radioactive waste. Different radioisotopes possess wildly different half-lives, ranging from fractions of a second to thousands of years. For instance, looking at common workplace and research isotopes, tritium has a half-life of 12.4 years, while carbon-14 takes 5,730 years to decay by half. Conversely, isotopes used in medical or biological applications decay much faster. SUL-PHUR-35 has an 87.4-day half-life, PHOS-PHORUS-33 is 25.6 days, PHOS-PHORUS-32 is 14.3 days, and iodine, 125 decays in just 60.1 days. Knowing these specific decay rates helps safety managers calculate current activity levels and establish appropriate risk timeframes. Despite its hazards, Ionizing radiation is an essential tool utilized across many modern industries. But where exactly is radiation used? And why do workers encounter it? From medical diagnostics and power generation to industrial quality control, radiation provides unique solutions that no other technology can match. However, using radiation in these sectors introduces occupational exposure risks for staff. In the following slides, we will examine the key industrial, research, and medical applications where radiation plays a pivotal role and why rigorous occupational hygiene measures are legally required. One major application of controlled radiation is in power generation, such as in nuclear facilities. Laboratories and academic research facilities frequently use ionizing radiation for analytical and diagnostic purposes. Advanced scientific equipment, such as X-ray diffractometers, electron microscopes, and particle analyzers, relies on controlled radiation beams to analyze material structures at the molecular level. Researchers may also handle unsealed radioactive sources during biochemical assays. Occupational hygiene in laboratory environments focuses heavily on containment protocols, correct beam alignment, personal protective equipment, surface contamination monitoring, and preventing accidental exposure to stray X-ray beams or active isotopic materials. Radioactive tracers are widely used in environmental monitoring, geology, and industrial process evaluation. Field technicians wearing specialized protective suits and respirators deploy small amounts of radioactive material to trace groundwater flow, detect underground pipeline leaks, or track pollution dispersion. Because these workers operate outdoors or in uncontrolled environments, they use field survey equipment to continuously measure ambient radiation levels. Occupational hygiene protocols and tracing applications prioritize airborne contamination control, personal monitoring, proper handling procedures, and thorough site decontamination following field operations. The medical field is one of the largest consumers of ionizing radiation. Healthcare professionals use X-rays, fluoroscopy, CT scans, and nuclear medicine procedures to diagnose illnesses, view skeletal structures, and track internal organ function. Additionally, high-energy radiotherapy is used to target and destroy malignant cancer cells. Doctors, radiographers, and medical physicists face daily exposure risks. Maintaining occupational health in hospitals requires stringent shielding, such as lead-lined rooms and aprons, along with strict adherence to the ALARA principle, keeping exposure as low as reasonably achievable. In manufacturing, radiation is used for non-contact quality control through industrial thickness gauges. In paper, plastic, or sheet metal production, a sealed radioactive source is placed on one side of the moving material, while a Geiger-Müller detector tube sits on the other. As the material passes through the rollers, the detector measures the amount of radiation penetrating through it. If the material thickens, fewer particles reach the detector, prompting automatic machinery adjustments. Hygiene controls here focus on source containment, mechanical shutter integrity, and preventing worker access to the primary beam. To control exposure, we must measure radiation accurately, starting with activity. The SI unit for radioactive activity is the becquerel, abbreviated as BQ. 1 becquerel is defined as exactly 1 atomic disintegration per second. This unit measures how active a radioactive source is, regardless of the type or energy of the radiation emitted. A higher becquerel count indicates a higher rate of decay, meaning more particles or waves are being emitted into the surrounding environment every second, directly influencing the level of hazard present. To account for biological impact, we use the equivalent dose, measured in sieverts. This is calculated by multiplying the absorbed dose by a quality factor, which varies based on the type of radiation. This table shows the quality factors for various radiation types. Photons and electrons have a factor of 1, while alpha particles and other heavy nuclei carry a higher factor of 20. Beyond the equivalent dose, we also calculate the effective dose. This is determined by multiplying the equivalent dose by a weighting factor that depends on the specific tissue type being exposed. Here are the weighting factors for different organs and tissues, ranging from 0.01 for skin and bone surface to 0.12 for bone marrow, lungs, and other organs. Minimize radiological hazards. Safety standards emphasize restricting exposure, duration, and frequency. Under Regulation 11 of the Ionizing Radiations Regulations 1999, annual dose limits safeguard individuals based on age and role. Adult employees 18+, 20 millisieverts effective dose, 150 millisieverts for eyes, and 500 millisieverts for skin and extremities. Trainees, less than 1/8, 6 millisieverts effective dose, 50 millisieverts for eyes, and 150 millisieverts for skin and extremities. Members of public, 1 millisievert effective dose, 50 millisieverts for eyes, and 50 millisieverts for skin and extremities. These tiered legal limits strictly ensure overall workforce and public radiation safety across all regulated environments. Monitoring workplace radiation requires specialized instrumentation, such as the classic Geiger counter shown here, specifically a vintage Victorine survey meter. Geiger counters operate using a gas-filled tube that ionizes when hit by incoming radiation, creating an electrical pulse. The meter face displays real-time radiation exposure rates, allowing occupational hygienists to quickly identify active radiation fields, detect leaks from shielded containers, verify safe working distances, and perform safety surveys in environments where radioactive materials are actively handled or stored. Top diagram: a closed radiation film badge dosimeter displaying an identification number 123,456. Bottom diagram: the open film badge displaying its internal components, labeled photographic film sealed in thin plastic on the left flap, alongside various filter windows on the main body. Alpha particles are heavy, positively charged subatomic particles consisting of 2 protons and 2 neutrons emitted during radioactive decay. Due to their relatively large mass and double positive charge, they have low penetrating power and can be stopped by a single sheet of paper or human skin, making them easily blocked. Beta particles are high-speed, high-energy electrons or positrons emitted during radioactive decay. Because they are much lighter than alpha particles, they have greater penetrating power and can easily pass through paper or outer human skin. However, they can be effectively blocked and stopped by a few millimeters of aluminum. Gamma rays are high-energy electromagnetic radiation emitted from atomic nuclei during radioactive decay. Lacking mass and electric charge, they possess extremely high penetrating power, passing easily through paper, human skin, and aluminum. Effective shielding requires dense, thick materials like centimeters of lead or several meters of concrete to stop them. Exposure to ionizing radiation carries both immediate and delayed health risks. Short-term deterministic effects manifest quickly as direct cellular damage and acute radiation sickness. Over time, prolonged or high-dose exposure can lead to long-term stochastic effects, including increased risks of cancer, genetic mutations, and adverse reproductive outcomes. Internal hazards occur when radioactive materials enter the body, allowing emitters like alpha and beta particles to directly damage living cells. Entry primarily happens through 3 pathways: inhaling airborne dust or gases, ingesting contaminated food or water, or direct skin absorption and wound penetration. Strict containment protocols are essential to prevent entry. To contextualize exposure, Health Protection Agency data compares radiation doses and associated mortality risks. Living in Cornwall carries an annual dose of 7,800 microsieverts, while a brain scan delivers 5,000 microsieverts. Lower exposures include a transatlantic flight at 69 microsieverts, down to everyday activities like eating 135 grams of Brazil nuts at 10 microsieverts. Radiological protection relies on 3 core principles: time, distance, and shielding. Minimizing exposure duration, maximizing distance from sources via the inverse square law, and using dense shielding like lead or concrete effectively lowers radiation doses, ensuring worker safety and keeping overall exposure as low as reasonably achievable. Protection against radiation hazards relies on containment and shielding. Containment completely encloses radioactive materials within physical boundaries to prevent contamination spread and inhalation or ingestion risks. Shielding places protective barriers, such as lead or thick concrete, between workers and external radiation sources to absorb energy and reduce dose rates. Distance is a highly effective radiation protection measure, governed by the inverse square law. Doubling the distance from 1 meter to 2 meters reduces the dose rate from 1 to 0.25 microsieverts per hour. At 4 meters, it drops further to 0.06 microsieverts per hour, demonstrating how small spatial increases significantly lower exposure. It restricts exposure duration and frequency. Thank you.